Now you can also think of, in typical cases, you don't find atoms tied to a rigid body, but two atoms tied with a bond, right? So now these two can describe a rotation. For example, if I'm displacing this body, let's say atom A and atom B, this side, this gets displayed like this, and then you have a rotation motion like this. Else, it can also do a rotation like this. But that rotation does not bring a change in the orientation of the molecule. It doesn't look like, especially in case of quantum objects, it doesn't look like as if anything is happening to the molecule. Another is like, so basically, axis which is perpendicular to the bond axis, this axis and this axis, both are perpendicular to these bond axis. So the rotations can happen only about these two axes, not about the internuclear axis. That rotation is not counted. So energy required to create these kind of rotations are very, very small, and typically are in the range of 1 to 200 centimeter inverse. Energy of radiation required to rotate. And now this energy falls in microwave region of the electromagnetic spectrum. Falls in microwave region, right? So hence this is called as rotational or microwave spectroscopy. Okay. So also we should also note down here that the molecule, but will not go into those details, but just for completeness I am mentioning, a molecule may not rotate about any arbitrary axis. There is a law called principle of conservation of angular momentum. Which dictates only few rotations are possible. So this is not in the scope of this course. So you will find this discussion in a spectroscopy course, or you can actually go and study any spectroscopy textbook. You will find details of this. But for completeness, I'm just mentioning it here. Only few rotations are possible. So we should also mention that a pure rotation spectra can only arise when the molecule has permanent dipole moment. So why dipole moment is required? We will see that. So dipole moment, basically what you are doing is you are trying to let the electromagnetic radiation interact with the rotating molecule, right? Now there should be some sort of interaction which should happen. Now that interaction comes because of the dipole moment. We will see how. So let us consider a rigid diatomic molecule. See, this has nothing to do with group theory. I'm just giving you a basic spectroscopy introduction because you have not gone through spectroscopy course. Okay. So this has nothing to do with group theory. So this is true for any general spectroscopy. So let us consider a rigid diatomic molecule with masses m1 and m2. Okay. So rigid means that the bond length is not going to change. So it's like a rod. Okay, there is no vibration which we are considering here. Okay, rigid means no vibrations. And the length of this is r, which is from the center of the two atoms. So this length is r, and let us say that the center of mass is c. Then you can call it as r1 and r2, distance from center of mass to the center of atom. So just like a rigid atom which is tied to by a thread, like a bar pendulum which is tied by a thread to a rigid body support. So now this atom is actually moving about this rigid support. So here the atoms are moving about the center of the mass. Okay, so the motion is about the center of the mass. So that's why we have considered somewhere in the middle. We don't know where it could be. It will depend on the individual atom. If it's a homonuclear, it will be in the center. If it's heteronuclear, it will be depending on the overall mass distribution, right? Now, independent rotation of this molecule can change the orientation. Okay, so let us consider a molecule actually. Let us consider a molecule with permanent dipole moment. Dipole moment we should all be aware of. We have already discussed the application of group theory in dipole moment. So dipole moment is separation of permanent unbalance of charge in the molecule, or separation of charges, right? So if it is a HCl molecule, so you have a positive charge, let's say proton, and a negative charge, let's say a chloride, right? Now if this molecule changes its orientation by undergoing rotation, so let's say you come to this position, so you say plus minus, right? And then you go opposite, you go minus plus, and again you go opposite, you go minus plus, and again you go. So it's a periodic motion, right? Periodic motion. Plus minus, like this. Now if you try to see, if you try to draw the direction of the dipole or the vertical component of the dipole, you get something like a wave. So if I'm trying to draw the vertical component of the dipole, you will get something like this. So it will be negative here, 0 here, let's say, because the vertical component is 0, vertical component is downwards, something like this. Here it is like this. So vertical component is 0, vertical component is now upside, right? So you will get something like this, 0 again, negative, and 0 again, right? And now if you try to match these points, you will end up getting a sine wave. So what you have drawn here is vertical component of dipole. So basically it tries to create some sort of a fluctuating electric field around it by doing this rotation. Now if you provide electromagnetic radiation which is having same energy, so the two waves, if they are having same energy, they will tend to interact, and in that sense that once this light is interacting, it will cause a change in the rotational frequency or rotation of this molecule, right? So thus any EM wave matching in frequency of this wave can couple to this rotation or rotational motion, we can say, and interact through its electric component. So once it interacts, there will be a change in rotational energy levels, and if there is a change in rotational energy level populations, then you will see that there will be a rotational spectrum. Okay, so if you see homonuclear molecules, no dipole moment, for example H2 gas, right? There is no dipole moment and no rotational spectrum. So a spectrum can come only if there is a permanent dipole moment, right? That we have already seen. Okay, so now let us try to work out a formula where we can use rotational spectroscopy to determine the bond length of the molecule. Okay, so use of rotational spectroscopy to determine bond length. So we have defined center of mass, right? So there was a center of mass somewhere in the middle. I said let's call this as center of mass. You have R1, R2, M1, M2, and this whole distance is R, right? So all the distances are from center of the atom. Now center of mass, how do you define where is the center of mass? Center of mass is defined by equating the moments on both segments of the molecular axis. What do I mean? So I mean that we can say M1 R1 is equal to M2 R2, right? So mass into the corresponding distance from center of mass should be equal to mass into R2. So if the two masses are equal, R1 will be equal to R2, and hence it will come in the center. If the two masses are not equal, it will be proportional to the masses, right? Also, let us also see what is the moment of inertia like in here. So the moment of inertia is defined by, so what is moment of inertia? It's a quantity that determines the torque needed for a desired angular acceleration. So moment of inertia, let me write down, it's a quantity that determines the torque needed for a desired angular acceleration. Also, it is a additive property. That means if there are multiple atoms in the molecule, so moment of inertia about the center of mass will all be additive. So that will give you the total moment of inertia of the molecule. So what do I mean? So it means M1 R1 square. So this is, it is also called as second moment of mass. First moment of mass is force, which is M1 R1 equal to M2 R2. The second moment of mass is moment of inertia, which is M1 R1 square plus M2 R2 square. Okay. So as I said, this is additive property, and moment of inertia is calculated about the center of mass and it is calculated for all the atoms present in the molecule. So here we are talking about a diatomic molecule. So both the atoms will contribute to moment of inertia. Now we also know m1 r1 equal to m2 r2, so I can always write it like this: m2 r2 r1 plus m2 r2 square. I'm trying to decrease the number of variables here. Okay, so I have substituted m1 r1 equal to m2 r2 here. Since m1 r1 is equal to m2 r2. All right. Sorry, I can also do the same thing here. m1 r1 r2. Okay. So now if I take r1 r2 outside, I will get m1 plus m2 over here, right? Okay. Also, I can say m2 r2 is equal to m2 r minus r1, right? So now I can substitute r2. So let's see. So I can say in this equation m1 plus m2 into m1 plus m2 into r1 can be written as m2 into r, right? So then I can also say r1 is equal to m2r divided by. So this is a basic algebra, nothing fancy about it. So you're just playing around with two equations here, m1 plus m2, and similarly r2 can be written as m2r m1 plus m2. So now what do we have here? So we'll get now expression of I can be now written as m1 m2 r square. So I'm trying to eliminate r1 and r2 here so that we can get to the expression of bond length. So r upon m1 plus m2. Substituting these two into the top one, r1 and r2, if I substitute, you will get this, right? Okay. Now this can be written as mu r square. Now what is mu here? Where mu is equal to m1 m2 divided by m1 plus m2, or we can say 1 by mu is equal to 1 by m1 plus 1 by m2, and it is also called as reduced mass. So I is equal to mu. Basically now it looks like as if you have reduced the diatomic molecule into a monatomic molecule tied to origin or a rigid body without any mass. So all the mass is now concentrated into one body and the distance is from origin, right? So something similar to bar pendulum case now. All right. So then we can say that the rotation of a diatomic molecule is equivalent to rotation of a mass mu at a distance r from the origin C, right? So now there is no center of mass. The whole thing is now concentrated about the single atom. So we have reduced the problem to one variable. Okay. So now again, I'm going to use the result of Schrodinger equation directly. I'm not going to go into details of how do you get that. So the quantized rotational energy levels for this diatomic molecule The maths can be a little boring, but the end result is very fantastic. So just bear with me a little more. Is given by Ej, where J is the rotational level and E is the corresponding energy of that level, is equal to h square upon 8 pi square I and j plus 1. Okay, where J is the total angular momentum quantum number. So again, I'm not going to go into those details. Now the transition between the two J levels is given by delta E. The energy difference between this is given by, and the selection rules actually tell that the transition can only happen between two consecutive J levels, that is Ej plus 1. So you can only talk about these energy levels when you talk about Ej plus 1 to Ej, or Ej plus 2 to Ej plus 1, and so on and so forth, right? So for general case, let us look at Ej plus 1 minus Ej, which will be equal to, if you do this calculation, so you will have h square upon 8 pi square I j plus 1 j plus 2. So now I have, instead of j, I have written j plus 1. So this becomes j plus 1, this becomes j plus 2 minus j plus 1, right? And this can also be written as h nu or hc by lambda, which is the wavelength of the light which we are using, right? The microwave here. Okay. It can also be called as hc nu bar, right? So now we have this expression for delta E. So nu bar, if we want to just talk about nu bar, so hc will come down. So you will have h upon 8 pi square IC, and in the brackets here you have 2j plus 1. If you solve this, you will get 2j plus 1. hc will come down, so you will get nu bar is equal to this. Okay. Now you can also write this as b times 2j plus 1, where b is equal to h upon 8 pi square IC, right? All right. So if you see that all of these are constants here, so if you determine B, you can determine I. If you determine I, you can determine R, which is the bond length, right? So let us see how from spectroscopy you can determine the value of B for any given molecule. I mean, not for any given molecule, for molecules which will show a rotational spectrum. Okay. So now for J equal to 0, the nu bar can be calculated as 2B. J equal to 1, nu bar is equal to 4B. J equal to 2, nu bar is equal to 6B, and so on. So that means if you look at the transitions, J equal to 0, J equal to 1, J equal to 2. So this spectral line would come at 2B nu bar number, right? Nu bar is in centimeter inverse. So this will come at 2B difference. So this can be obtained from, like, you can put in the value of J equal to 0 and then you will know this is 2B. Similarly, you will get 4B here. And if you keep on going, you will get 6B and so on, right? So separation between spectral lines in a rotational spectrum is equal to 2b. So that means you can determine, once you record a spectrum, you will notice that the difference between the spectral lines will be equal to 2b. Of course, we are talking about only pure rotational spectrum. Okay. So once you see that this difference is 2b, you can determine the value of b. Once you have determined the value of b, you can determine the value of I. The reduced mass can be determined by theoretical values because you know the mass of the atoms, and hence the bond length can be determined just by looking at the rotational spectrum, right? So we can say from spectra you get the value of b. Mu can be determined theoretically, and thus R can be calculated, right? So this ends today's discussion of rotational spectroscopy. Next class we will take up similar introduction, of very brief introduction. This is no way a comprehensive introduction because this is not a spectroscopy course. So we'll give a brief introduction of vibrational and Raman spectroscopy, and then we will move to the application of group theory to spectroscopy. Okay, that is all for today. Thank you.